Hello everyone, section 10.3, using chords, example 1. In the diagram we are told that circle P is congruent to circle Q, that segment FG is congruent to segment JK, as marked in the diagram. We're told that segment arc JK is 120 degrees. We want to find the measure of arc FG. Alright, so these two circles are congruent. The congruent chords, congruent corresponding chords theorem tells us that congruent chords within the same or congruent circles have congruent arcs. So arc FG is the same as arc JK, so the measure of arc FG is 120 degrees as well. Example 2. Find the measure of segment KH, which is over here. A diameter that is perpendicular to a chord bisects the chord and its arc. So if NK is 14, then NH is also 14. And if NH is 14 and NK is 14, then KH is equal to 28. Again, a diameter that is perpendicular to a chord bisects the chord and its arc. Don't forget that it bisects the arc as well. That's in the theorem. You don't have to prove that. It's in the theorem. It's already been proven for us, and that shows up on an assessment. So that means that these are equal to each other. 2x minus 8 equals 127 minus x, add 8, 3x equals 135, x equals, let's see, 3 goes into this, 45 times. So if x is 45, we're looking for HLK, that's all the way. So 90 minus 8 is 82. 82, making this 164 degrees. Example 3. Telephone company plans to install a cell tower that is the same distance from the centers of 3 different towns, P, Q, and R. Where should the cell tower be placed? So we actually have seen problems like this. We saw problems when we were doing centers of triangles, when we were doing the incenter, the circumcenter, the orthocenter, and the centroid. And we learned that the center of the triangle that is formed by the perpendicular bisectors of the sides, called the circumcenter, is equidistant from the vertices. And the reason that that's true, and we talked about that back then, is that it's the center of the circumscribed circle, so it's hard to draw. The circumscribed circle, I know I drew that light on purpose because it's just hard to see. But if I do the perpendicular bisectors of PQ and the perpendicular bisector of QR, then this is going to be the center of that circumscribed circle. And we know that because of what we learned back when we were doing the centers of triangles, but we also know it from this section, the congruent corresponding chords, the perpendicular chord bisector theorem, okay, which says that if you, the converse of the perpendicular bisector theorem, if you are on the perpendicular bisector of a segment, then the center, then that is a diameter of the circumscribed circle, right? So this is a diameter, this is a diameter. If we have two diameters and they're meeting, they have to be meeting at the center. It's the only point that they could ever have in common. So this is where we're locating that new cell tower. Example 4. In the diagram, EP is equal to EQ, and they're both 12. CD is 5x plus 7. AB is 7x minus 3. Find the radius of circle E. So because these two chords, AB and CD, are equidistant from the center, they're congruent to each other. Okay? Because they're congruent, we can write the equation 7x minus 3 equals 5x plus 7. Okay? Why do we need this? Well, this is going to get us the value of x. Once I get the value of x, I'll be able to know how long AB is, which will tell me how long PB is, half of it. Then I'm going to draw in my radius right here, BE. I could do BC or EC, I could do ED, I could do AE, any one of them, they're all the same. So I'm going to have 12, I'm going to have the value of BP, and Pythagorean theorem is going to give me the radius BE. So subtract 5x, I get 2x, add 3, I get 10, x equals 5. So if x equals 5, then AB is equal to 5 times 7 is 35, minus 3 is 32. And half of 32 is 16. So BP is 16. So this is a 3, 4, 5 multiplied by 4. So 3, 4, 5, making BE 20. Radius is 20 units. Okay, example 5. Circles A and B are congruent. CD is a chord in both of the circles, so it's a common chord connecting points C and D, which are on both circles. AB is 8 inches. Can't really draw that into the picture too hard. CD is 6 inches. Okay. How long is the radius? Well, let's draw one of the radii. I'm going to draw AC. It's one of the radii. AC's got to be the same as AD, because they're in the same circle. It also has to be the same as BC and BD, because they're in congruent circles. So the radii of congruent circles are congruent. What type of a quadrilateral is ACBD? ACBD is a rhombus. What do we know about the diagonals of a rhombus? Diagonals of a rhombus are perpendicular, and they bisect each other. So if AB is 8, then this part is 4. If CD is 6, then this part is 3. And yet again, we have another 3, 4, 5. Radius is 5. Okay, example 6. I think I should be able to fit it in on the side, the left-hand side here, this proof. Statements, reasons. Statement 1, recopy the given. I can do the squigglies, you cannot. You have to recopy it. What is the given? The given that we're given circle O, and we're given that CE, which is a diameter going through point A, is perpendicular to segment BD. Okay, because it's perpendicular, we know it bisects. What else do we know? Well, we know CF is congruent to itself. We know this is a right angle and this is a right angle, definition of bisectors. We know all right angles are congruent. We know these two triangles are congruent by side, angle, side, side, angle, side. These two triangles are congruent. These two sides are congruent by CPCTC. Congruent chords have congruent arcs. And there's our proof. Let's write it out. So statement 2, let's say angle CFB and angle CFD are right angles. Definition of perpendicular. Statement 3, angle CFB is congruent to angle CFD. Right angles congruence theorem, or all right angles are congruent, either the name or the theorem itself. Statement 4, FB is congruent to FD. That's our perpendicular chord bisectors theorem. Statement 5, CF is congruent to CF, reflexive property. Statement 6, triangle CFB is congruent to triangle CFD, side angle side. 7, I'm going to squeeze this in here. I've only got 2 more lines left. Segment CB is congruent to segment CD. CPCTC. And finally, statement 8, arc BC is congruent arc DC by the congruent corresponding chords theorem. Congruent corresponding chords theorem. QED. Example 7. CD is tangent to circle O, which means that we have a right angle here. Lines AO, BE, and CD are all parallel. Parallel, parallel, parallel. OF and FC are equal to each other, and they're both 6. Now I know it doesn't look like it in the diagram, so I'm trying to scale. That's 6. That's 6. Okay. How do we get the length of OE? Well, OE is a radius. OC is a radius. OC is 12. OE is 12. How do we get OD? Well, because these are parallel, all transversals are broken proportionally through parallel lines, 3 or more parallel lines. Always divide transversals proportionally. That's a theorem that we had back when we were doing parallel lines, back in chapter 4, I think, possibly 3. If that transversal is broken up congruently, then all the transversals will be broken up congruently. This one is being broken up into 6 and 6 congruently. This has to be broken up into 12 and 12. Again, I know it doesn't look like it, which makes OD equal to 24. A little bit tricky here. We're going to find the measure of angle D. So the measure of angle D is right here. The measure of angle D is part of triangle COD. COD and this is the angle. Well, we'll get there. It's a right triangle. COD is a right triangle. This opposite side is 12. The hypotenuse is 24. If you want to do right triangle trig and do inverse sine, because we have opposite over hypotenuse, if we do inverse sine of 6 over 12 or inverse sine of 1/2, you're going to get the measure of angle D is equal to 30 degrees. We can also recognize that it's a 30, 60, 90 right triangle. Recognizing that's a 30, 60, 90, this is 30, this is 60. If this is 30, this is 30. If this is 30, this is 30. Our goal is to get the measure of arc AB. Arc AB is equal to the same as this measure here, E something else. They have to be congruent to each other. Why do they have to be congruent? Because of the parallel lines again, and this is being broken up evenly. Okay? Or we could say 60, 30. If I drew this in here, this is perpendicular. This is being bisected. This is 60. This is also 60. 60, 60, and 30 is 150. How much is left? 30 degrees. AB is 30 degrees. FE, right here. This is 6. This is the short leg, 60. FE is opposite the 60, making it the long leg. 6 square root 3. Arc BE. Arc BE is right here. It's being intercepted by 60 and 60. 60 and 60 make this 120 degrees. Example 8. If OJ is 12, find the length of JK. Well, let's take a look at OK. OK also has to be 12. 2 radii. Let's draw in the perpendicular bisector. Perpendicular bisector makes this 60, 60. Makes this 60. So if this is 60, if this is 12, the short leg, this is 30. Short leg over here is going to be 6. If this is 6, this is 6 square root 3. This is 6 square root 3. And JK is equal to 12 square root 3. And that's the end. Thank you very much. Bye.